Welcome to Chapter 3, Descriptive Measures. Now, in this chapter, you're going to see some formulas, and some of them may look rather complex. But fortunately, in today's world, we have calculators and we have spreadsheets. And the focus of this course is on spreadsheets, specifically Excel, to do a lot of these calculations where the formulas are pre-done or built in. So we can simplify things a great deal. So we're going to talk about central tendency. Where's the middle? We're going to talk about variation. How wide is the distribution? And what is the shape? We're also going to talk about something called a box plot. And we're going to provide summary measures for, you can see, population, and then something called covariance and coefficient of correlation. So how closely to the two does one cause an effect on another? And how well our line that we're going to draw is a good measure of what's going on with, say, a trend. Central tendency is about the middle. And we're going to talk about the 3 M's, which we'll get to in a moment. Variation or dispersion has to do with width. So you have where's the middle, you have how wide is your distribution. And then we're going to talk about various shapes. Is it symmetrical? Is it skewed? Is it to the left? Is it to the right? And things along that line. So this is a formula you're looking at. Whoa, wait a minute. What is this? This is mean. This is calculating the average. And so that's represented for a sample by the X bar. So you simply total up all the values and divide them by the number of observations. So if there's 30 students in class, you take the 30 scores, add them together and divide it by 30, and you get the average. So I would focus less on the formulas, which are, again, built into Excel. There is an average function built into Excel, so you don't even need to know what the formula is. And so in this particular case, it's just showing you some of the tendencies here, where you have 5 values, you total them up, the average is, or the mean is 13 on the sample on the left. Then you have 5 values on the right, and the mean is 14. So it seems like they're pretty similar. But you can see they look quite a bit different. There's a big gap between the 14 and the 20, even though the mean is only increased by 1. So it can be affected by what I've referred to earlier in the lectures as outliers. Outliers are simply extremely high values or extremely low values. And you have to be careful of them because they can distort your data. Now, a median is the true middle. You know what a median is. You've driven down the road and you're trying not to hit the median. So if you have a median on a 4-lane road, 2 lanes going one way and 2 lanes going the other, the median is the center. So it's almost like a 5th lane that nobody's supposed to drive in because it's usually got trees or cement or things like that. So you try not to hit the median. So it's the middle. So you can see in this particular case, you have 5 values on the left. The median is 13. That's the 5 values on the right, even though the mean changed last time. The median for both of these sets of data is 13. So it's not affected by the outlier. When you read about things like housing prices in Calgary, they use the median. The reason for that is, let's say one month you have an unusually large number of $1 million homes selling. So let's say that you have 12 in the month of August. That will drag the average up. But then in September, you only have 2. So that the average will look like it's going way down. So you're allowing a very large value in that case to affect the middle. So the median is much more stable because it's not as drastically affected by outliers. And so you can see at the very bottom, it's less sensitive than the mean to the extreme values. And that's actually really important. You're trying to get a real sense of where is the middle. So, you know, students always ask, what's the class average? What's the class average? Well, there's been times when I've had students not even write the test. There's some, you know, or they haven't written it yet. So they're still enrolled in the course. They don't write the midterm, so they get 0. Well, that drags the average. So let's say you have 30 students and 1 student doesn't write it, write the final, the midterm exam. That automatically drags down the class average by 3%. So let's say you have 3 people. They haven't officially withdrawn from the course, but they don't write the midterm exam. So 3 and 3 and 3, rather than your class average being 74, it's now 65. So just because 3 students didn't write it. Now, should you include those 3 students? On one hand, yes, they're still enrolled in the course. They just didn't write it. But that would be an extreme low outlier. So the median position is you take the number of positions, add 1 to it, and divide it by 2. And if the number is odd, the median is the middle number. So in the previous example, we had 5 positions, plus 1 would be 6 divided by 2, which is 3. So it would be the third from the left. It'd also be the third from the right. It's truly in the middle. So 2 values to the left, 2 values to the right. The third value is the position 3, not value 3. And if it's even, then it's the average of the 2 middle numbers. So what you would have is, let's say there's 6 positions. So you'd have 6 plus 1 is 7, divided by 2 is 3.5. So you take the value from position 3, add it to the value from position 4, and divide by 2. So you sort of make a new number that isn't actually part of your array. So here's an example of a mode. A mode is the most frequent. It occurs. It is not affected by extreme values, and you can use it for categories or numbers. There may be no mode. There may be several modes. So in the example on the left-hand side that you're looking at, you can see the mode is 9. A mode has to have a frequency of more than 1. So we actually have 3 possibilities: 5, 9, and 12. All occur more than 1 time. But 9 is the mode because it occurs 3 times. 5 and 12 only occur twice. If you had another 12 value, you would have what's called bimodal. You would have 9 and 12, so they both be 3s, a frequency of 3. So you can have bimodal, trimodal, or polymodal. So that, but it has to be more than 1. So you can see on the right-hand side, all the values occur only once. They're all unique. Don't say the mode is 0. You will get that as a mark. There is no mode because 0 is a value, not a position. So in this particular case, the one on the left, the mode is 3, and the one on the right is not 0 mode, it's no mode. So be prepared to answer a question, which I usually ask. Give an example like on the right, what's the mode? One of the answers is 0, and that's wrong. 0 is not the mode. None or no mode is correct. So in this particular case, we've got a list of housing prices. We calculate the mean is 600,000. The value of the middle position, because there's 5 of them, is 300, and the mode is $100,000. So they all give us different values, and they describe the data differently. So it's not just about average. The most reliable is actually median. So if you really wanted to show that you knew what you were doing, and you're sitting in a meeting, somebody says the average price is this. Depending on what the distribution looks like, you might ask them, what was the median price? People look at you like they either don't know what they're talking about, or if they really know what they're talking about, they're going to say, that's a very good question. The median is actually more important because it doesn't react, or it's not as sensitive to the extreme outliers. All right. The mean is generally used unless there are extreme outliers. So if you use mean, you are assuming that there's no extreme outliers. If there are, it's going to make the mean fairly meaningless. But a lot of people use that just because they know what it means, or what the definition is, and they assume that there's no outliers, which can be very dangerous. And some places do both. We'll talk about the mean housing price and the median housing price. So you have the central tendency. We're not really going to talk about geometric mean. It's the same as arithmetic mean, except for the fact that it deals with it's exponential. It's a curve. So arithmetic mean in finance would be simple interest. Geometric mean would be compound interest. Variation, range, variance, standard deviation, and coefficient of variation. So it has to do with width, dispersion, or distribution. You can see that the two curves that they have, or the two distributions they have, look very different. One is very peaked and very narrow, and the other is much wider. So there's a much wider range in the class average. My goal would be have a narrower range, but have the mean as high as possible. I don't want 20, 30, 40, 50% of my class failing. And that could be with the wider distribution. Oh, I might be a great instructor for 20% of the class, but the other 80% just don't get it. So the range is very simple. You simply take the largest number minus the smallest number in your ordered array. So 13 minus 1 is 12. It tells you any of the numbers range from 1 to 13. So the difference between the two is simply the range. So you can see the range on the values on the left is 5. And it's same as the range of the values on the right. But it doesn't look at how they're distributed. Remember, we're trying to describe the shape. And the range can also be very sensitive to outliers. As you can see, the range in the second bullet point, the range is 4. When you look at the numbers, they're all between 1 and 5, okay. But then you have the same thing, except rather than 5 being the high value, you have 120. So now all of a sudden the range is 119. Even though all the other values literally are the same, except for those two values on the far right-hand side of 5 and 120. So that would, wow, a range of 119 compared to a range of 4. It's all because of one extreme outlier. So variance. Variance has to do with my second favorite 4-letter word, risk. In finance, which I also teach, you use standard deviation. The higher the standard deviation, the higher the level of risk. The lower the standard deviation, the lower the level of risk. In finance, if you have two companies, Company A declares a dividend of $4 in year 1 and $0 in year 2. That averages to be $2. Company B, or number 2, has a dividend of $2 in year 1 and $2 in year 2. The average is 2. The standard deviation for the first company with the 4 and the 0, like what's going to be the dividend in year 3? Well, anywhere from 0 to 4 for the first company. What's going to be the dividend for the second company? Well, it's 2 and 2. It's probably going to be close to 2. So there's more certainty or less uncertainty. And again, this formula is going to be done. We used to, until a couple of years ago, use calculators for it, and now we're going to use Excel has it built in to calculate sample variance. Sample standard deviation is simply the square root of the variance. So variance and standard deviation are almost identical. So if I give you a standard deviation, you square it to get the variance. If I give you a variance, you need to take the square root. So if I give you a variance of 9, the standard deviation is 3. If I give you a standard deviation of 9, the variance is 81. Again, Excel has this built in. Now, somebody might actually ask the question, why do you have both? Because variance has no context. So if I give you the number of 9 and it's a variance, it's just 9. It is not $9, 9 days, 9 anything. But if I give you a standard deviation of 9, whatever the original data was in. So if the original data was money, that's say $9. If it's in miles or kilometers, or that would be in kilometers. If it's in height, it would be in, say, centimeters. If it's time, it would be in seconds or minutes or hours or whatever the original data is. So variance is useful, but not used a lot because it's a number with no context. There's no dollar sign, there's no percentage, there's no centimeters, there's nothing to it, where standard deviation is very, very important to statistics. And this just tells you how to do it. But honestly, you don't even need to bother with this. You know, all these steps are just done for you. One of the things that by using Excel, we will simplify the tedium. And also, this is the way it's done in industry. If you sit there with a pen and paper and a calculator, not only will your coworkers laugh at you, but when I talk to my students who graduated, not only will they laugh at you, you will not have a job because you cannot keep up. And people share things electronically. Student after student that I talk to about it, we use Excel. We use Excel. We use Excel a lot during the day. And you need to understand how to do things on a spreadsheet if you want to. I don't care if you're in marketing or accounting or finance or supply chain or just general business. Use of spreadsheets and understanding basic tools like charts, how to draw charts, how to calculate standard deviation and mean and variance and some of the other things we're going to talk about. Critical you do know how to do it on a spreadsheet. So you can see here's the formula. Don't bother with it. We're gonna have something called a data analysis tool pack that's built into Excel, and I'll show you in the examples how to use it. And it has these formulas built in. All you got to do is select the data and select what you want to do, like calculate descriptive statistics, and it calculates all this for you. So you've got the mean, the standard deviation. So you can see the mean is the same in all of them, but you see that the standard deviation for data set C is the largest. And even just looking at the distribution, you can see that the mean for data set B is tightly clustered together. For data set C, it's very wide, as is data set A, but C has the most amount of variation. There's fewer points that are close to the middle. So if this was finance, company from data set C would have the highest level of risk. Data set B would have the least amount of risk. The smaller the standard deviation, the narrower it is. The larger the standard deviation, the wider it is, as far as the distribution, what it looks like. Okay, and as you can see, just as I said, the more the data spread out, the greater the range, the variance of the standard deviation. The more the data is concentrated or closer together, the smaller the range, the variance of standard deviation. If all the values are the same, there is no variation. So if all your values, like the standard deviation for the dividend that was 2 and 2, I don't need a calculator. Standard deviation is 0. There's no variation. Even if it was $1.99 and $2.01, you would have a small variation between the dividends. All right. Z-scores, which we'll use a little bit in this course, but because we're focusing on samples, you will have, we're going to deal more with something called t-values or t-scores. And so standard deviation of a Z-score, we used to use a lot, but now that we have more advanced technology, we're going to use t-values because Z-scores are for populations normally. And t-scores are for samples. And I said earlier in the lectures, we almost always have a sample, not a population. So this is the formula. We're going to have a function in Excel that will actually calculate not only the z-score, but we're also going to have a function that calculates the area underneath the curve. So once again, it takes a lot of the tedium out of having to calculate the z-scores. We can either have the Excel do that for us, or what's even more important is what area underneath the normal distribution curve does a standard deviation of 1.3 represent. So you want to find out how the data is distributed. We're also going to talk about skewness. This is lopsidedness. Okay, you either have symmetric, which means even on the left and even on the right, or skewed. It's either left skewed or right skewed. So it's either got a tail to the right, which is right skewed, or a tail to the left, which is left skewed. Kurtosis. In the previous slides, you saw one distribution that was fairly flat and one distribution that was fairly peaked. The flatter one is called platykurtic, and the peaked one is called leptokurtic, which you're going to see. So left skewed will look like this. It has a tail on the left. Symmetric, there is no tail. It's even, 50-50. And right tail, the tail is to the right. So it's where the tail is, not where the peak is. And one other way to look at it, if you don't have a diagram like this, look at the mean. The mean is below the median if it's left skewed. The mean is equal to the median if it's symmetric, and the mean is to the right of the median if it's right skewed. So you don't even need the chart. You just look at the mean. So if the mean's 90 and the median is 87, the mean is 90, is higher than 87, it's right skewed. If the mean is 80 and the median is 87, the 80 is below the 87, it's left skewed. If the mean is 87 and the median is 87, it's symmetric. So here's what I was talking about before. Just a minor little point. Leptokurtic, there's a function for calculating kurtosis. So if the kurtosis is greater than 0, in other words, positive, it's leptokurtic, which means it's peaked, which means it's narrower. It's mesokurtic, which means it's not peaked nor flat. And that's the kurtosis is 0. If the kurtosis is negative, it's platykurtic. So those are some things that normally most people don't know. It just describes, you know, if you see something that's really peaked, it's lepto. If you see something that's fairly flat, it's platy. In my own little mind, the way that I remember this is platy, flatty. That's how I remember it. So platykurtic is flat, leptokurtic is the other one. So it's the opposite of flat is peaked. And very rarely will something be mesokurtic. So it'd have to be exactly 0. So we're going to do box plots and the 5-number summaries. We're going to deal with quartiles, breaking things into quarters. The bottom quarter, Q1, the next quarter, which would be from, say, 26 to 50, that would be Q2. Then from 50 to 75 is Q3, and then above 75% is Q4. So here's just what I was talking about. So you break it into segments. So the middle part, Q3 minus Q1, is called the interquartile range. It's where the 50% of your data represents. So the above Q3, there is no Q4. That would be like above 100%, which is impossible. So if you want to look for people who are in the top 25%, then you're looking for people who are above Q3. Where would you use this? Years ago, when I took a course in compensation, how to pay people, I remember this. and I wish I would have known it sooner, but 90% of people, actually 95% of people, rate themselves in the top half. So Q2 to the right. 95% of employees say they're above average, and you know that that is not possible. 95% of people that are above average is 50%, so it doesn't fit. But also, to break it down into quartiles, I remember the number, 75% of people think they're in Q3 or above Q3. So if I say to you on the side, if I come around the class and I say to you, it's like, oh, so like you're an average student, you're above average. 95% of students, I believe, will say they're above average. And if I say, you know, are you just above average or are you like well above average? I say that 75% of students are well above. Well, we know that mathematically that is not possible. So again, this is like what we did in probabilities, finding the position. So you can take n, which is the sample size, plus 1 divided by 4, divided by 2, divided by 4, and it gives you the rank value, although the bottom one you have to multiply by 3. All right, so here's some, if you get an average, you average between the two data values because it gives you a position. So here's just some examples. You've got an ordered array from 11 to 22. The range is 11, 22 minus 11. The mode is 16, but we want to break it into quartiles. So in this case, there are nine values or positions. There are plus 1 divided by 4, 2.5. So position 2.5 is halfway between value 2, which is position 2, and value 3, which is position 3, and you get value 12.5. So 11 and 12 are in Q1. All right, where is Q2? It is the 5th position. So in this case, the 5th position is, and Q2 is also known as the median. So don't be surprised if you get that on a test. The median is also known as Q1, Q2, Q3, or the mean. It's also known as Q2. So that would be value number 16, which would be 11, 12, 13, 16 is the 4th, but 16 is also the 5th one. So there's 4 values to the left, there's 4 values to the right. So it's the position in the middle. And Q3, you can see, works out to be position 7.5. So that would be position 7 is 18, position 8 is 21. You sum the two and divide it by 2 to get the value of 19.5. So you take the value of 18 plus the value of 21 and find the middle of the two. IQR, interquartile range, Q3 minus Q1. It represents the middle 50%. So here is an example where you're given some data. Interquartile range, the highest value is 57, the lowest value is 30, the IQR is 27. So simply take the value at Q3 minus the value at Q1, and 50% of my values are between 30 and 57. 25% of my values are above 57, and 25% of my values are below 30. So the 5 numbers are the smallest number, Q1, Q2, Q3, and largest. And you will get this on your assignment and your test. It'll ask you for the 5 numbers summary. Smallest, Q1, Q2, Q3, largest. The numbers will get larger. X smallest will be the smallest number. The second smallest number is Q1. Then the next number is Q2, Q3, and Q4, or Q3, and then largest. So you go from the smallest number to the largest number, and you can see some of the symmetry, right skewedness, left skewedness. Just pay attention to the mean. If the mean is to the left is the smallest number, it's left skewed. If the mean is to the right or the highest number compared to the median, it is right skewed. If the median and the mean are the same, then there's no skewness. All right. So you can see in this particular data, there you got your 5-number summary, smallest, Q1, Q2, Q3, and largest. And this is the representation of where it is, the data is skewed, because the 25% on the left is a larger area than the 25% on the right. All right, they're symmetrical in this case. And you can present the box plots, as you notice, either horizontally, as this one is, or vertically. I personally tend to prefer them horizontally. It just, I don't know, for my choice, but it doesn't really matter. You will get that. So here's again some examples what the box plots will look like. So with the large area, the left skewed, you will see the large area in the box, which the white area in the box is left skewed. Where the large area in the box is on the right, it's right skewed. And when they're even, you have symmetry. All right. So in this particular case, you can see just looking at it, your 5-number summary is 0, 2, 3, 5, 27. And you can see visually that this is right skewed. The area in the box that's from 3 to 5 is larger, of course, than from 2 to 3. So the data is right skewed. All right. And then, so we just talked about sampling. The mean for population is defined by the Greek letter mu, which is sort of the funny looking U sign, but it's done the same way. Again, in this course, the vast majority will be sample means, sample populations, sample variances, sample standard deviations. So this area is I'm going to go over fairly quickly. It's not, it will be used when we have proportion or percentages. We will use it a bit. Population variance. Here's the formula. You will be given both. Just be careful to read which one. Population standard deviation is also the square root of the population variance. So here's a nice little summary. The one on the right is the important one. X bar is the mean. Sigma squared is variance. Sigma or S is simply the standard deviation. So the ones on the right are more important than the ones on the left. But be careful that you know what the ones on the left represent. The empirical rule is something that we use for, as you can see, the symbols are populations, not samples. Although as the sample gets larger, it gets closer to the population. We'll talk about that in an upcoming chapter. So in this particular case, one standard deviation under a symmetric distribution, one standard deviation is 68%. Plus 1 minus 1 standard deviation represents 68% of the area under the normal distribution curve. 2 standard deviations is 95%, and 3 standard deviation is 99.7. It's actually 99.73, but those are the values. So 1 standard deviation is 68, 2 is 95, and 3 is 99.7. And so we'll use that later in the course, but we're going to use a lot more where we use the t-values. But the t-values will be very similar to the z-values as the sample size gets larger. And as I said again, the reason we're using t-values, not z-scores as much, is because when we start to use Excel, it can calculate a z-score or a t-score more easily than the old-fashioned way when we had tables. Chebyshev's rule, the information does not have to be normally distributed. And so it has a slightly different formula. It uses K for the standard deviation. So 2 standard deviations, you can see the formula, is 1 minus 1 divided by 2, or the k, squared, and then you turn it into percentage. So 2 standard deviations would be 1 divided by 4, which is 0.25. Subtract that from 1, you get 75%. So it's a little more conservative. If you're not sure that your data is normally distributed, then you would use Chebyshev. But remember, we have statistical analysis to be able to calculate the mean, the mode, the median for thousands or hundreds of thousands of pieces of data, where that would have been basically like a huge task that wasn't possible. If you have, 140,000 pieces of data, good luck finding the average if you're punching in your calculator. It doesn't work. It would take you a long time. But with today's technology, it doesn't matter if it's 140,000 or over 100 million. It can be done in very short time. So we talked about central tendency, variation, and box plots. And we use it to describe populations, and we use it to describe samples. And we did a little bit on covariance and coefficiency, but not much. So just don't worry about that. So I hope you enjoyed chapter number 3. Thank you for your time.